Hmm?
I didn't know if I got this, but obviously. So,
Yeah, I mean, you might be able to use it on your laptop, but I don't know.
no, it's fine. I'll just.
With the camera, how it is, you can point at the slides and people can see where you're pointing. So
Yeah, that's true.
yeah, some of the fireworks last night.
Yeah, they were very nice.
It was cool, yeah.
It was nice because they tricked you to think that it was done, so people would start
Yeah.
clapping, and then it would start again for like 5 times.
Yeah.
It was fun.
Was there like, did Renault bring you guys inside after it was over, or did you just go after?
Oh, that was good.
Irene's gonna come. I saw her earlier, so.
Yeah, I had a meeting with her this morning, so.
Sometimes she joins online.
But I have to give a seminar on Thursday about the same thing.
Ah,
So she might just
yeah. Nice. Well, this is a good warm up then. Right, so why don't we get started? So, hello everyone. Welcome to this week's network seminar. So this week we have Maria, who's a DPhil student with Irene and Renaud. It's just those two, right?
And Scott from
Physics.
Matthew.
And she's going to tell us about some work she did for her master's thesis. So yeah, welcome and take it away.
Okay, so my thesis aimed at exploring how you could use networks to analyze the dynamics of phenomena in the atmosphere, which turned out to be the polar vortex, which we'll hear about in a second. But I first wanted to introduce why you would want to use networks to analyze atmospheric flow, because it's not the most common way of going about it. So you can think of the atmosphere as a complex system in which large-scale interaction between different parts of the fluid can give rise to collective behaviors. So, for example, we can have that phenomena that are very separated in the atmosphere can be evolving coherently, or we can have that a distribution of forces really affect the dynamics at a specific point, or that we have very similar flow patterns in disconnected part of the atmosphere. And these phenomena are quite hard to analyze because of the high dimensionality, multi-scale dynamics, and nonlinearity of fluids or the atmosphere. And complex networks gives us a nice way to simplify this very complicated continuous system into a discretized graph. And if that graph is expressive enough such that it's representative of the state of the atmosphere, then we can use that to do a lot of things. So, for example, we can uncover connectivity patterns. It's a lot easier to see how the fluid is connected. We can measure the influence of individual flow patterns in the rest of the dynamics. We can cluster similar flow regions, many other things. So now I'm going to introduce the specific atmospheric phenomenon I was looking at. So this phenomenon happens in the stratosphere, which is the second layer of the atmosphere. So we live in the troposphere, and it consists of vortices, that is, flow spinning around an axis, around the poles, in this case, for the vortices. And they are very powerful, they're cold, and they go in the direction of the Earth spinning, so they are westerly, go from east to west. And a very nice way of visualizing them and tracking its evolution is using potential vorticity, which is just a measure of how that fluid is spinning. So there's several ways of measuring that. So the most straightforward way would be to take the curl of the velocity field. That would be relative vorticity. Then you can also take into account the spinning motion of the Earth. So you have to take into account the Coriolis effect, and that would be absolute vorticity, and then potential vorticity takes into account the Coriolis force, but also the mass distribution of the fluid parcel. So basically the main point is that this quantity is conserved as long as you don't have heat going into your system or heat going out of the system. So because of these nice conservation properties, it's very nice to plot the polar vortex. And when you plot it, you see the polar vortex as a region of high PV, surrounded by a region of less PV, that we call it the surf zone. And then when we go into the other hemisphere, then PV is almost near zero. So it's just like a blob of PV on top of your planet. And it is formed during the winter. So it's formed because at winter you don't get that much solar radiation going into the atmosphere, so it cools down and it forms these jets. So it starts forming in autumn, then it peaks in the winter, then it dissolves in the spring. And it has a lot of impacts. So it impacts circulation, it impacts chemistry, and it also impacts our climate and weather. So it's very nice to study. So the biggest events that can happen in the polar vortex are sudden stratospheric warmings, which is a big disruption of the vortex that you can see. And these are caused by some waves that are created in the troposphere, and they move upwards. And when they break or dissipate, they give some momentum to the polar vortex that leads to erosion of the vortex. And then if we keep sending these waves up, then it will lead to a disruption. So we have two different types of disruptions. We have displacement events, in which the polar vortex displaces a little bit from the poles. So the axis of rotation is not exactly at the top anymore. But those events and these events have some dynamics that vary a lot in height. And then we can have speed events, which is when the vortex fits into, like the video there. And in these, the dynamics are very horizontal. So that's quite nice because we can use a 2D model instead of a more 3D model to simulate that. And that's why I focused on those. And it also leads to increasing temperatures and a slowdown in the winds. So that is what I'm studying. Now I'm gonna quickly present the model. So since it's mainly horizontal, we model the atmosphere as a thin fluid layer. And the two main variables that we have is velocity, so V, and then the thickness of that layer, which is the phi, so that's just the gravity times the thickness, but you can think of it as. And the things that were taken into account is the pressure gradient. So if your height goes up like this, then it will try to go down. So that force, then we have the Coriolis force, because the planet is rotating. Then this is just that flux going in must equal the height that you get in a certain point. And then we have two forcings that we are going to set, so we get a polar vortex. So we can express these equations in a simpler way, not simpler, but a more conventional way, which is the way modelers typically present them as. So it's basically the same, but velocity instead of having velocity, you represent it as vorticity and divergence. So the top equation will model your vorticity, the second divergence, and then the heights. But you still have the same forcings. And now we're going to specify them. So we have, for the radiative forcing, we have the relaxation towards the state we want. So we want a blob of PV at the top, then a surf zone, and then almost nothing in the southern hemisphere. So this is that, just driving the system towards that state. Then we have the topography, which looks like this. So it's like hill, and then a valley, and then a hill, and a valley. And this is what's gonna create the waves that are gonna disrupt the vortex. So this is what's disrupting and what's gonna create sudden stratospheric warmings. And we have a parameter that's A0, which is the amplitude of that forcing. So if we increase this, then it's gonna be more disruptions. And this is the term that you just need to get what you want, but it's not very useful. So forget about it. So we solve this numerically for different forcing amplitudes. We get different regimes. So when the topography is very small, we have a very clear vortex. Then when the topography gets more important, then we start getting sudden stratospheric warmings. And then at the end, the forcing is so big that we don't get it. And during my talk, I'm going to refer to this regime as the general behavior for specific A0, and then a state as the different configurations it can take. So it can be, you can have a vortex, or it can be splitting, or you can have no vortex, but those all happen in the. So we're done with fluids. Now we can do networks. So I'm going to quickly screw through graph theory because you already know what the network is. You don't need to. So I'm going to use weighted networks. And then the measures I'm going to use is density and clustering coefficients for global measures, and then for centrality measures, strength, velocity between them. And I just chose the simplest ones because we didn't know a priori which ones were going to be the most relevant for the system. So there wasn't any reason to choose a very fancy metric. So now I'm going to be dealing with two types of networks. We have the linear networks and the Lagrangian networks. I'll start with the linear. I think it's the most straightforward way of thinking about it. So in the linear networks, nodes represent fixed geographical regions. So if this is a fluid, then we can discretize it, and then we assign a node to each geographical region. And then in each region, we will have a time series of the climatological variables of that part of the fluid. And with that, we can build edges. There's several ways of building edges. I'll do that using correlations. So edges will be statistical connections and also plasticity. So edges will be simple interactions between the two regions of the fluid.
Just saying, what's the time series? What does it describe? Time series?
Yeah, I'm going to show it in a second, because for the different types of edges, you'll use a different time series. So for correlation-based networks, edges represent statistical connections, and we choose PV, which is the plasticity metric, and we choose this because it's the most straightforward way of visualizing and thinking about the dynamics of the vortex. But you could also do it with other variables, and it's probably going to give you the same results if you use a different one. But in theory, for this case, you could use a different one. We just chose this one because it's the most representative of.
Because that's the edge.
That's at each node you have that time series, right? at each node, you have a time series of the velocity at that point through time. So for example, if you're considering a month of data, and at each node, you have a time series of the velocity throughout the month.
Okay.
Yeah. And then we are gonna build the edges based on the statistical connections between the different time series of each node. So
maybe I just don't understand still what it is.
I guess what is the high value of PV?
oh, okay. So a high value of PV means so high value of velocity, absolute velocity, would be that your fluid is spinning very fast.
So is that in speed?
So it's the curl of the wind speed.
Sorry?
The curl?
Yeah.
Of the wind speed. So it's how it measures how much it's spinning. And to that, you can take into account that Earth is spinning as well.
Yeah.
So you have like an extra spinning motion because of Earth is spinning.
And how can you measure that for a single point?
So you solve the equations I showed before, you solve them in a grid.
Yeah.
So at each grid point, you have the evolution of PV at that point. So you have at each time step, you have the value of velocity throughout your whole regime, and then you have that through a lot of time steps. So you just take one, like you focus on one region, and then you take the value throughout the whole of the simulation. Yeah, so I chose to use the Pearson correlation coefficient, which is just the covariance of the two time series of your nodes divided by the square root of the pi. Which means if you have so it goes between -1 and 1. If it's 1, it means that the two time series, if one increases, the other one increases. If it's negative, it means that if one increases, the other one decreases. And then if it's 0, it means that it correlates. And this gives us a measure of how coherent two nodes are. But because information takes time to travel throughout your domain, if you want to study information flow, then you need to add the time. Because, for example, if you have a vortex here and then it travels through your domain to this point, then these two time series will be very correlated when you timeline them. So when you check that they are. And then we can build the edges based on this. So for this intelligence, for the correlation coefficient, we just say the absolute value of its the correlation coefficient, and then we're not going to allow self-interactions, and we're going to discard non-important interactions above the threshold. So if, for example, if you choose 0.5, then everything that's below 0.5 wants to get.
Sorry,
No.
just stupid, but I'm still stuck with this measure of movement.
Yeah.
Like why is it not just like speed of wind? Like why wouldn't you be able
Well, it's quite hard to. I mean, you could do it with the speed of wind.
Yeah.
It's just that for this particular phenomenon in the atmosphere, then this measure in particular is quite descriptive of dynamics.
But if you were to want to do just like connectivity network,
You could use, for example, height as well. And
so
then
height of-
the velocity. You could say velocity. And
Yeah.
then you can just see the time series of velocity throughout your simulation and see if the velocity is correlated. Yeah.
So one of the edges are positive.
Yeah, they're always positive. And then
Something that maybe you'll get to in the results, but do we like expect the instantaneous one to be not useful? Like, is it just being set up as a comparison because the time delayed one is what we want? Or like, is there some reason that the instantaneous one is also?
yeah, no, it is useful because it measures how coherent it is instantaneously. It's just a different type of information that you get. But I did actually do more analysis of the instantaneous one because it's simpler than the time delayed. Just the time delay shows you the direction of how your information is traveling throughout.
And presumably there's no good way to choose the delta T.
Yeah.
Is there a good way to choose the delta T for the time delay, or do you just sweep?
Oh, so I swept. So I chose delta T, like I considered a maximum delay that you could have, and then I just in here. In here, you just choose the maximum throughout that range.
How do you choose the threshold?
So I didn't put it here. It's in the extra slides if you if you're curious. Yeah, because it's a little bit it doesn't tell you much, but it's not complicated, but it takes a little bit of time to. And then for the time delayed, it has to be above a threshold, but it also we only build an edge if between J and I if J precedes I. So you get a direct. Yeah, so then for this one, you get an undirected network, and this one is directed. So we can, this is an example of a network you might get. So if we select 300 days of simulation, then we can split it in sliding windows of 25 days. And then for each window of 25 days, we get a network. So this is what we're plotting here. So if we take an example topography, so 0.15, which is the simulation here, and we get the instantaneous and the time delayed networks, and we can plot them in different ways. So we can plot the orthographic projection of the centrality measures. In this case, I'm plotting strength. So this gives us at the top the strength of coherence of your nodes, and then below I'm plotting this out strength minus the in strength. So out strength will mean that there's a lot of information going out of the node. In strength will mean that there's a lot of information going into the node. So if you subtract them, we'll get that red nodes will be driving the flow, and then blue nodes will be being driven by the flow. Does that make sense?
Can you quickly, when you were looking at the time delay, are these the results across all time delays or for a fixed quantity?
So you consider, for example, 7 days, and then you check on those 7 days which time delay will give you the maximum Pearson correlation coefficient.
The maximum.
Yeah.
Okay.
Yeah, and then we can see how the strength. This is well, actually, I'm going to show you one thing when this gets to. So when it splits in here, we can clearly see how information is traveling from where the vortex was split to the other side. So it goes from red to blue. And then this is a plot of the distribution of strength in your nodes. So at each point, plot box plot of the strength that you get, and we can see that as the vortex is growing, the strength of your network the nodes of your network is growing, and then when it splits, it goes down, and then it goes up again. And we can do this. So I'm going to focus now on the instantaneous correlation, correlation coefficient, and we're going to plot it for different values of topography. Yes.
So in the instantaneous network, you have strength.
Mhm.
Does this essentially mean how much local correlation there is?
Yeah, it's like how strongly correlated that node is
With its neighbors, right? With all the others, right? So when it peaks or when the strength values are high, that means that there is some order to what's happening. And when they're very low, it means it's just all random. Thank you.
You said that for the time delay one, you sweep through all the time delays and choose the maximum.
Yes.
Does that mean for different edges, but different time delays at which you?
Yes, because for example, when the vortex splits, you're gonna have a vortex that moves around like this. So you want, like, these nodes are not gonna be correlated to these nodes at the same time lag as these nodes are gonna be correlated because the vortex is moving.
So that means information from the network happens at different paces over different edges.
Yeah. Okay, so we plot density, and density will be like the average correlation of your flow, and we can see, okay, from top to bottom, This is very small topography. This is very high topography. And then if it's green, it means that the vortex is stable. If it's yellow, it means that the vortex is growing. If it's red, it means that it's splitting. And then if it's gray, it means that it's dissolved. So in these plots, we can see what are the centrality measures at each state of the vortex. So we can see the density when the vortex is growing, it goes up a lot, and then it collapses. So it's quite similar to the strength. Then we observe similar thing for the global clustering coefficient. So this gives you the tendency of the network to form coherent structures. So when the vortex is stable, we get a lot of nicely organized networks. When it's growing, it gets increasingly organized, and when it splits, it goes down. And then when it's dissolved, there's almost no structure to the network. Then with strength, we see the same thing as before. So when the vortex is stable, we have substantial strength, but it's not the biggest values of strength that we'll see. And that's because the vortex is coherent, but it's not resonant. So the theory is that when the vortex becomes resonant with the forcing, which means that the forcing has a lot of vortex, then it's when it splits. And we see this when it's growing. So when it's growing, it gets like very, very correlated. And that's representative of resonance. And then when there's no vortex, then quite low connections. And then finally, we get the closeness and betweenness. So closeness means how related your node is with the flow as a whole. And then betweenness is the extent to which your node acts as a bridge between two zones that are not coherent between them. So when the vortex is stable, we get low closeness, not high, but higher betweenness, which means that your network is split into communities that are quite tightly connected, but they're not connected between them. Then when there's no vortex, we observe the opposite. So everything is linked to everything. There's not that many bridge nodes. So we can have a wedge of weak interactions, strand of weak interactions. And then when it's growing, we see that nodes get increasingly closer to each other, and betweenness goes down. So the network becomes increasingly connected. And then is that okay? Then instead of selecting laser column, instead of selecting like I don't know 25 days on, we can select the whole simulation. And during this whole simulation, the vortex is going to go through all of the different states and not through all the different states, which means that the network that you get as a result is going to be representative of the regime dynamics and not the state dynamics. So it's going to be all of the states in your regime are the same. So
Would you tell us the simulations you're running are continuous space?
Yeah.
And then you've discretized it. How many nodes are you using roughly? Just
like 8,000 or something. Yeah, so for small topographies, we have a very coherent vortex, and we can see I'm only plotting the strength here. I also have plots of the network metrics if you want to see the but yeah, so for the instantaneous, we can see that the vortex is quite split into very coherent structures and then less coherent structures, so it's quite organized. And from the time delayed network, we can see that information seems to be flowing from the inside to the outside of these coherent regions. When it gets slightly more elliptical because of the topography, then our network represents how it becomes this, takes this shape, so it's more elliptical. Then when we start getting splitting, then the most coherent regions are always the vortex, and then the areas to which the lobes of the splitted vortex travel. And from the time delayed version, we can see that information is traveling from red to blue, which means this is the area of the vortex splits. and then it travels like this to the blue, and it's the opposite at the bottom, so it splits here and then it travels to the blue. We see that for the different regimes, but it's becoming weaker as stronger. Then when there's no topography or very little topography, then we get a lot more correlation at the top and bottom. So these are some anticyclones, and it's definitely just going like around them. There's a lot of correlation and not that much. Well, I mean, there's still a lot at the bottom, it's still coming, but it's similar order of magnitude, and we still see it going from red to blue like this. So we know that information still travels mostly from the split effect. And then finally, when there's no strength, okay, so in conclusion, for the correlation networks, we've seen that they are representative of the system dynamics, and we can extract meaningful insights. So we can quantify its evolution, and we can see how patterns of coherence and information flow change as we increase. Then we can build vorticity-based networks. So in this case, we do have to take a specific time series, which is from relative vorticity, which this is just the curl of the vorticity. And we can approximate the vorticity distribution to be, so we have a continuous field of vorticity, and we can think of it as concentrated in n point vortices. So the field that we get will be the field approximately that you would get if you had n point vortices at your nose. And we take the magnitude of those vortices to be the that point, and then it's multiplied by the area it covers, because the network is not covering people there. So it's the areas at the poles are a lot smaller than the areas at the equator. So the vortices at the equator must really stronger. And we can prove, but I won't let you go through the whole proof, that this is true. So the velocity that Vortex J, so Vortex at node J is inducing in Vortex at node I is given by this, which is just a function of how strong the vortex is and then how they are located. And then we can build a network such that the connections between J and I is going to be how much velocity J is inducing in I. So, yeah.
That's like a one-step kind of influence, right? Like you then don't include that induced vortex in your calculations for the nodes.
Yeah, so this is a simplification. There's a lot of things that you're not taking into account.
I guess, like, do you think that you lose much with that simplification?
We'll see. But yes, obviously, I mean, the point of networks is that you have a very complicated fluid and you want to simplify it in a way that it's a lot simpler, but it's still representative of your atmosphere. So it could be the case that this is so simple that it's not longer representative of the state, and then it's not very useful. Yeah. So in this case, the networks are not fully connected anymore. Oh, sorry, they're not thresholders. So that means they're fully connected because all of the things are going to have a weight, which means that all of these.
Do you expect any zeros or not with this function?
Not really.
No.
Because
So
you
it's
always
really
gonna-
only connected.
which means it takes a lot of space in your computer. But yeah, so all of these metrics are not very useful anymore because they're going to be constant and equal to what it would be for completely connected. So we're only going to look at strength. And in this case, the strength in is how much velocity is being induced at your points, and then the strength out is how much velocity is inducing in other points. So again, we take an example simulation, and then we can build we can have orthographic projections of the strength. And we can clearly see the vortex. So the tips of the vortex are inducing a lot of plasticity in the field, and then there's a lot of velocity. There's a lot of velocity being induced in the surroundings of the vortex, which is quite in accordance with the physics, which is that there's a very strong jet winds going around. And then we can more or less see that this strength increases as the vortex grows and increases when it splits, but it's a lot less sensitive than the correlation. So maybe in this case, it's too simple to train what the numbers are going on, or at least this metric doesn't.
In the left-hand plot, which is presumably from
This one?
yeah, that one, the leftmost one. That one's presumably the simulation itself.
Yes.
And then the second one is the network measures.
Yes.
In the simulation, it seems fairly like red in the center and then less red as you go. But in the network, there seems to be rings.
Yeah.
Right? Is that an effect of the discretization, or is that like something cool that the network's showing us?
So, I mean, this simulation is not, I think perhaps I should have plotted all the velocity. So the velocity that's just the call of the velocity field, so because I think it's gonna look a lot more similar to the other.
Nice. So you're measuring different things on this.
Yeah.
Okay.
It's just to see at what state the vortex is in. And then we can see how the vortical interactions change throughout the different regimes. So when the vortex is very circular, there's not that much velocity being induced by the vortex. But as it gets a more elliptical shape, then the tips induce a lot of velocity. And when it starts facing the same. And then when there's no vortex, then most of the velocity being induced in the fluid comes from outside the vortex. So in conclusion, again, we see that it's retains some information, maybe not as much as the correlation networks. That the evolution is somewhat sensitive to the state of the vortex, and that we can detect how vortical interactions change throughout the different regimes. And finally, I'm going to look at Lagrangian networks very quickly. So in Lagrangian networks, you get your velocity fields, and then you can trace some particle trajectories throughout your fluid, and then each particle is going to become trajectories of your network. And then you can build a matrix. I'm going to explain what it is in a second, and then you get your very nice. And this is very useful because it can help us get Lagrangian coherent structures from the fluid, which are persistent patterns in the flow that affect how traces are travel throughout the fluid. So in this case, for example, we would expect to get a coherent vortex, and then we will expect to get some particles being stripped out of the vortex. So the way we...
So is one of these trajectories, just to try to compare Eulerian, like a path on the Eulerian one, which you would see constantly, let's say between these geographical locations, would be like a trajectory, right? Yeah. So here, if we say, so essentially the nodes here correspond somehow to paths on the Eulerian net. Is that fair to say?
Yeah, maybe. Yeah, I haven't thought about it like that, but yeah.
Cool.
So the way we build a matrix is that we do it based on dissimilarity. So we do that with distance. So basically, two trajectories that remain very close together will have small dissimilarity, and two trajectories that are very far away from each other will have big dissimilarity. And then the way we cluster them, but now we're going to try to divide them in different groups, is maximizing the dissimilarity between the different clusters. So we have this parameter that has your adjacency matrix and the cluster assignments, and we want to maximize this. So when the dissimilarity is very big, we want SI and SJ to be distinct, so this is big, and when it's very low, we want them to be quite close to each other. And then we get a measurable similarity between two nodes, which we can use to do that.
What's SI? Is that just 1, 0? SI minus SJ?
No, it's a continuous thing.
Also, the clusters are continuous clusters.
Yeah. So this can be rewritten as an eigenvalue problem. And you can get the clustering assignments solving an eigenvalue problem with the graph fashion, and then each corresponding eigenvalue corresponds to orthogonal function. So the first one is very good at separating your flow, but then the next one is good, but it's not as good, and then the last one is quite bad at separating your different trajectory. And once we have these, we can split the graph into two groups per eigenvalue. So each eigenvalue gives us metric of similarities towards to pull the different trajectories towards. And we do that using aggregative clustering. And then, since we have done that for every eigenvector, I'm only considering the first three, because how would you do it for all of them? We can combine these splits to give you different. So, for example, if you have the flow here, the first eigenvalue was split like this, so it looks like it's placing the lower bit on the top bit, and then the second eigenvalue here seems to be taking out the particles that are leaving the vortex, and then here we have the vortex, and then the this like particle going in circles at the bottom, and then here we have split the vortex completely and thing at the bottom, and then a similar thing goes down. Yep. So if we do this for all of our regimes, at the beginning we get a very coherent vortex, and then when it starts splitting, we get the vortex in the middle, then particles being stripped to the left and to the right, then the anticyclones at the top and at the bottom, and then this vortex gets increasingly small. The topography gets more important, and then at the end we don't have a vortex anymore, and we just have these two lobes. Yeah, so in conclusion, we retain simple information again, and we can use them to finally. I found that the strength of using networks is that it's quite simple to build. It's quite versatile because using a network you can capture very different types of interactions with it, and it's quite consistent. So the results that we get for Lagrangian or for toxicity based or correlation based all to each other, and they stuff what we found before. Some difficulties is that you get very dense and weighted matrices. You don't know a priori which metrics are going to be the most useful, and the physical interpretation sometimes are a little bit complicated to get to. And the main conclusion is that you can reduce your data into a network and retain some important information, and that this simplification can allow you to get some nice information about the dynamics that are going. Right. So in the future, what I want to do is improve the methodology. I want to try to compare with more classical methods, so I can see what the networks are giving us that those are not. I want to see if we can do skillful predictions of atmospheric behavior, and then see if we can use it as a tool to compare different types of models and observations. In particular, I want to look at the interactions between the stratosphere, so that layer where the polar vortex exists, and the troposphere, which is where we live, and see what the networks can understand that better.
Awesome. Thanks, Maria. So if there's more questions in the room, if anybody online wants to ask a question, you can raise your hand or type in the chat. I've got an eye on it here. I have more questions, so I can start.
I want to comment. I just want to say your visualizations are really nice.
I was also going to say that. Thank you for sharing your pretty pictures with us.
Especially when
So
I
nice.
imagine the,
Yeah.
like this is great.
So I was thinking when you showed the results for the second part of the correlation networks,
Yes.
like I guess the one where you're no longer thresholding, forget what you called it. The fully connected one. Like when we're looking at the box plots, like the statistic over time, I was maybe, or I guess sorry, I think I'm blending two questions. So I was thinking that maybe the reason you're getting, so actually it was the one where you don't have the thresholding. Yeah.
Oh, the toxicity one?
Yeah. If you did threshold, like
Yeah.
so here you're seeing like you do get like the variance is growing right before, and then there is like a collapse in the variance. Like there's tons of noise here, we know that. So like, did you look at or have you thought about trying to like measure these statistics, taking out some of the noise somehow? It's like vague. Like you could do maybe some statistics on this matrix to say like we're going to do some thresholding so that we can get a stronger result.
Yeah.
Just because there's so much, we know there's a lot of noise. And we see what we want, but it's not really very like.
Yeah, I think I didn't do it at first because you're kind of modeling you're modeling the toxicity fields, and if you'd say, well, I think I could maybe, I don't, because for the correlation one, you do get noise because you're measuring correlation, and maybe it's not like it's a linear correlation, and your correlation is not really linear. And there's some things that are not correlated, but it's too, yeah. But in this one, like the edges are quite like exact. Like it's not.
So the I guess the interpretation of noise is different in the two things, right? In the correlation, the noise is like, it looks like a correlation, but actually we know it's not. In this case, the noise is just that it's not actually important. So it's like peripheral more so than it's not real. Like I guess that's what I was thinking is if you could remove some of the periphery, then the strength statistic might look a lot stronger than it does.
Maybe I should try.
Yeah, go ahead.
Is it on this network?
No.
Okay, so I had a question about the previous Eulerian network, the one where you have threshold, and you tracked a bunch of network metrics, right?
Yeah.
So my question is that that one maybe that box plot. Yes. So I believe rho is density.
Yeah.
Density, clustering, strength, some.
Yeah.
And then there's two. Yeah. So have you here also thought about looking at, so when rho grows, when the density grows, there's more edges. So we would expect more clustering, right?
Yeah.
Simply by noise.
Yeah.
So have you checked A and B? If you haven't, that's fine. But what do you expect you would see if you have a null model? For example, for the global clustering, where you just say, if I have 1,000 edges, here's how many triangles I expect to see. But oh no, I see so many. So is that something you've done already?
I mean, okay, so the way I set the threshold was that the density was, or the average density was constant between all of, like each regime has a constant density. That's why they're all, when there's not a lot of variance in the density, they're all quite close to 0.5, because I set it so the densities would all, like the constant, like it would be constant. So you more or less, it's true that in these networks, the density fluctuates a lot because it's growing. But overall, the density of all networks should be more or less similar, which means that you get more or less networks that are as expressive or have more the same amount of edges. But yes, it is true that in these ones, it's not.
I'm just wondering for each individual row of boxes, how correlated, because they are correlated, clustering coefficients, all of these are correlated measures. So I'm wondering whether there's a way to remove, essentially put priors. I'm wondering if it's useful. And B, whether you think that'll change.
Yeah, no, because it's very clear that they'll go up and down.
But that's good because that's an
Yeah.
insanity check because that is what
Yeah.
you would expect.
Oh, but I can be thinking about it. I don't know right now.
Yeah, well,
That actually relates directly to my other question, which was about between us plot.
Yeah.
Which is why I was getting mixed up before. So I'm surprised not to see more sensitivity to betweenness, and I was wondering if it's exactly because of density somehow. Like, is there just too much density for the betweenness?
I
Okay,
think so.
because when I look at the pretty pictures, like the simulations, when they separate, like in the regime where they're separating, it looks like there should be a high betweenness,
Yeah.
like some edge should have a huge betweenness value relative to what it would, but then it doesn't show up in the statistic. So I was just wondering, do you think it's about the density or?
I think maybe it's about the resolution, so maybe I have too many points, and there's quite a lot of points that are in between the vortex edge, and there's not one that's like, I don't know, maybe there's one, I don't know. So if I had like one node in the vortex, okay, 3, and then 3 outside, then maybe there would be a lot of.
if you discretize more.
Yeah, maybe if I discretize more, then I would get more betweenness.
Or maybe playing with the threshold, I don't know if that would matter, but.
Yeah, increasing it.
Did you find like a scale of discretization where things start not mattering how much more continuous you make it?
I didn't play that much with the resolution.
Any more questions?
Yeah, how to determine the direction of information flow on the network based on some target
On the correlation,
direction?
yeah. So if you have, maybe it's easier if I just, if you have a vortex here and then it's going like here, then this might look like, oh, there's vortex and then there's no vortex, and then this one might look. So then you can try to overlap it. So when you switch through different time lags, what you're doing is you're considering the 0 like this, and then when you move it a little bit like this, and then at some point you get like the whole point side, and this is where you get your maximum. And when you get your maximum, you can see in which direction did you have to move this one to get a high correlation in this one. So if you had to move it backwards, it means that this one came first. If you had to move it forwards, then it means that that one came first. So if you have to move it backwards, then you set the edge like this usually. And then if you had to move it forwards, then you have to set it. Does that make sense?
Yeah. So basically, you can know the direction of the flow based on like that.
Yeah.
Great. No questions online, so let's thank Maria again. And as of now, we don't have a speaker for next week, so I'll send a cancellation if that's for sure. If anybody has a speaker in mind, feel free to send an email. Who could speak on very short notice? Go ahead and send an email. Otherwise, I'll send a cancellation later in the week, and we'll come back the week after. See everybody then.